In this video, we explore a special class of planar graphs called maximal planar graphs. So these are going to be maximal in the sense that the addition of any edge to the graph will necessarily make it non-planar. So let's take a look at some maximal planar graphs. Here are 5. We can have some small ones, right, like K2 is maximal planar simply because I can't add any edges to it. Same thing for K3. It's planar and I can't add any edges to it. K4, again, I can't add any edges to it, and if I had, I guess that's not important, but so here we have, looks like K2-3 with some edges added into it. Notice now if I add any edge, so finally we have a graph here where I could add some edges into it, right? So for example, this vertex and this vertex are non-adjacent, and there is no way for me to add an edge between those two vertices. Any edge I add would necessarily make it non-planar. I would have some crossing. Finally, here we have K2-2-2. And again, there are some vertices that are non-adjacent, specifically any two vertices in the same partite set. And if I added an edge between any two of them, I would add a crossing to the graph, and it would be non-planar. So this is what it means to be maximal planar. All right, so we need to establish some theory for this as well. So one thing to notice is that in a maximal planar graph, once we have it embedded in the plane, every region has to be a 3 cycle. So why is this? Well, let's say I have, some graph, I don't know, I have some stuff going on over here, blah, blah, blah. But let's say some subgraph of it, I have a region that has, that's bounded by something bigger than a 3 cycle. So something like this. Well, notice I wouldn't have any edges here in between vertices in the cycle. So maybe I'll actually just make this a concrete cycle, and I'll let you imagine a bigger one as well. So here we have a 6 cycle, bounded by a 6 cycle, but what could I do now? Well, if I have a 6 cycle, what I could do is I could add this edge in, and so right there we know that it's not maximal planar because I just added an edge in and it's still planar. So what else could I would do? I could add this edge in, and I could also add this edge in. And now it looks like in this 6 cycle, at least, there's no more edges that I could possibly add into this without adding crossings. And so at least this part is maximal non-planar. Right, and so we can do this and always end up with triangles. Any cycle that bounds a region, I can always add an edge in to make it make that boundary or that region now consist of triangles. I can triangulate it. So this is sort of the first big observation, and then we go back to, if you remember, the proof of theorem. What was this theorem? Theorem 10.3, I believe, where we were able to show that, right, for planar graphs. So remember, planar graphs, we have m is less than or equal to 3n minus 6, and this came from adding up the number of edges on the boundary of every region, and we knew that there were at least 3 edges on the boundary of every region. That's where this came from. So for maximal non-planar graphs, you might guess, did I say non-planar? I meant maximal planar, sorry. Maximal non-planar doesn't make any sense. Maximal planar, you might guess that this is actually equal to 3n minus 6. But we can't quite, because we know there are non-planar graphs with this satisfied, we can't simply say we could add edges to it and it wouldn't cross the threshold, and therefore it would be, not maximal planar. We actually have to construct a different sort of argument here, but it relies on this fact that every region is bounded by a 3 cycle. And so what that means, right, if I add up, remember our m sub i's were the number of edges around the boundary of every region. So if I add up the m sub i's, remember this gives me twice the number of edges. and I equal 1 to r, the number of regions. And if each m sub I, right, bounded by a 3 cycle, that would be exactly 3, and so this would give me 3r. So I have 2m is equal to 3r, and then by Euler's identity, I have n minus m plus r is equal to 2. Take that, multiply everything by 3 like we did the last time. 3r is equal to 6. Now I have 3r is equal to 2m. Substitute that in. I get 3n minus m is equal to 6, and which, of course, it follows that m is equal to 3n minus 6, exactly. So this is a nice result, that in a maximal planar graph, number of edges is exactly 3n minus 6. All right, we'll be able to do some work with this. So what else is true about maximal planar graphs? Well, if it's order 4 or more, then the degree of every vertex of G is at least 3. So how does this work? All right, so we'll be given a maximal planar graph of order at least 4, and let V be a vertex. And what I'm going to do is I'm going to remove it, in which case the resulting graph should be planar, and I have a theorem about planar graphs. And I'll put this together to recover that the degree of V is at least 3. So right, we start off, we know that m, our size of this maximal planar graph, is 3n minus 6. And then if I remove this vertex, G minus V has size. Well, what's the size of G minus V? Well, it depends on what the degree of V was, right? It's m minus degree of V. But I also know that the size, right, has to be less than or equal to 3n minus 6 because it's planar, right? G minus V is planar, so G minus V, so m minus degree of V is less than or equal to 3. Well, 3, not n minus 6. N was the number of vertices in my original graph. Here I've removed a vertex, so this would be 3n minus 1 minus 6. And let's see, so what does that give me? Here, m I know is equal to 3n minus 6, so I have here 3n minus 6 minus degree of V is at most 3n minus 9 when I simplify that down. Subtract 3n minus 6 from both sides and switch this around a little bit and see that 3 is less than or equal to degree of V. So the degree of V is at least 3 for every vertex. And of course this makes sense. If I had a vertex of degree 2 somewhere in the graph, and maybe I have some stuff going on over here, some stuff going on over here, well, there'd be some vertex down here, and I could add this edge in. So this sort of makes this idea completely rigorous. All right, so that's nice. And let's see, where can we go from here? So there's some other big results about maximal non-planar graphs, and in particular about their degree. So one interesting result is this one. If G is maximal non-planar of order 4 or more, then one of these things has to happen. Either you have a vertex of exactly degree 3, a vertex of degree 4, or 2 adjacent vertices of degree 5, or 2 adjacent vertices, one of which is degree 5 and the other is degree 6. One of these 4 things has to happen. Now this might seem like, I don't know, something tedious to prove because we have these 4 things to do. But we're going to see a proof technique here that's going to make quick work of this theorem. And this is using the method of discharging, which is a pretty interesting proof method on graphs. So let's take a look at how we can prove this. Right, we're going to use discharging. The first thing I want to establish is this formula in a maximal planar graph. That if I add up 6 minus the degree of every vertex, multiply, so I add up the sum of 6 minus the degree times the number of vertices of that degree, n sub I, then I'll end up with 12. So that's kind of an interesting result, right? So here n sub I is number of vertices of degree I. Delta is my maximum degree. I know that every vertex has at least degree 3, so I'm adding up from 3 to delta, adding up the number of vertices of each degree times the number of, or times the degree, or rather times 6 minus the degree of every vertex. And that'll add up to exactly 12, no matter what the graph is. So that's pretty neat. So notice there's some things here we can use, right? If I sort of pull this apart, notice I have, somewhere in here I have I times n sub I, and the sum from 3 to delta. Well, that's twice the number of edges. And then at the other part of that, I would have 6 times n sub I. And so where does that come from, that 6? So let's take a look at a proof of this. All right, so we know that if I add up I times n sub I from I equal 3, remember minimum degree is 3 in a maximal planar graph, up through the maximum degree delta, I'll end up with twice the number of edges, 2m. Let's see. And so what does that tell me? Right. Well, I also know that this is a maximal planar graph. And so I know that m is equal to 3n minus 6, right? We got to get some results out of this result. M equals 3n minus 6, so that means that 2m is equal to 6n minus 12. Oop, there's that 12, and there's that 6n. So 2m is equal to that, so I have now, putting these two things together, I have twice the number of edges is equal to 6n minus 12, so I have sum I n sub I from 3 to delta is equal to 6n minus 12. Now, this n, I want to get this as a sum, so n is equal to, think about this in terms of the n sub i's, it's just if I add up the number of vertices of each degree, right? If I just add up the n sub i's, I should get the number of vertices. And so I'm going to swap that out. So this tells me, okay, I have sum from 3 to delta, I n sub I is equal to 6 sum from 3 to delta of n sub I minus 12. All right, we rearrange this a little bit. I can pull this 6 inside of here. I have 6 n sub I. Let's add 12 over and subtract this I n sub I. I have 12 equals the sum of 6 n sub I minus I n sub I. That's the sum over all those. I pulled the sums together from 3 to delta, and that's equal to 12. And this is exactly the terms that we're looking for. So that's 6 minus I times n sub I is equal to 12. So there's that theorem. So what is the method of discharging? The idea is, where do I want to be when I talk about this? The idea is I'm going to assign essentially a label to every vertex. But what I'm going to call it a charge for a reason. I'm going to assign a charge to every vertex of 6 minus I. And then I know that if I add up the charges of all the vertices, I get exactly 12. So I know the sum of charges in my graph. And more than just assigning a label, I'm going to come up with a rule for distributing those charges, right? So we assign charges at the beginning, and then there's some discharging rule where the charges are redistributed throughout the graph. And that's it. And then I'm going to use properties of these charges, the fact that I know they add up to 12, and my discharging rule, things like this, to prove this result, that this is going to come from a method like that. So this is pretty wild. So we're going to start this theorem. This is going to be a proof by contradiction. We're going to assume none of these things happen. So no vertex of degree 4. So assume none of 1 through 4 happen, are true. So assume the graph doesn't have any of these. So what that means that in particular we have minimum degree of G is at least 5. That's one result. And then we'll use these 3 and 4 later on as well, that these don't happen. No two adjacent vertices of degree 5. Okay. So excuse me. So proof. So we assume none of these happen. I don't know why I'm writing this again. Assume none of 1 through 4 are true. All right, this tells us that in particular, minimum degree is at least 5. And we're going to assign a charge of 6 minus I to each vertex of G. So what does this mean? This means every vertex of degree 5 has a charge of +1. So vertices of degree 5 have +1 charge. Vertices of degree 6 have +0 charge. And vertices of degree k, for k greater than or equal to 7, have a negative charge of minus, so negative 7 minus, k minus 6, negative k minus 6. And I'm writing it just like this. I'm flipping it around just so you can see that these are k minus 6. These are all negative charges. And we know by that previous theorem, since I'm assigning the charge 6 minus I, when I add those all up, we know the sum of the charges over all vertices in the graph is +12. So already this seems a little bit suspect, right? That means I need to have enough vertices of degree 5 to contribute a positive charge in order to balance all of these high degree vertices that carry a negative charge. All right, so let's establish a discharging rule. So I've assigned all the charges to my graph now, and now I'm going to discharge. So discharging rule. What I'm going to do is I'm just going to look at the vertices of degree 5 that have +1 charge. So at every vertex of degree 5 with +1 charge. Well, I guess I don't want to say that because they all have +1 charge. Every vertex of degree 5 redistribute charges by moving. So I'm going to split this up among its neighbors. It has 5 neighbors and +1 charge. So I'm going to move +1/5 charge to each neighbor. All right, so this is the idea. Is I'm going to take my vertex of degree 5. It's got 5 neighbors. It originally had a +1 charge, and now I'm moving all these +1/5, +1/5, +1/5, +1/5. I'm going to move these along the edges to its neighbors. And I want to think about how did these vertices, so which vertices charges were changed. And so now this is going to have a +0 charge afterwards. So let's see. So now, after discharging, I'm going to move on to the next slide to make this a little bit less cluttered. So I want to again reevaluate where all my charges lie in the graph. So let's see. So every vertex. So after discharging the vertices of degree 5, every vertex of degree 5 now has charge +0. And then remember, none of 1 through 4 happened. None of these conditions happened. So what this is going to mean is my vertices of degree 6, sorry, it's taking a second. My computer's lagging a little bit. I'm going to have to restart after this. Two adjacent vertices, one of which has degree 5 and the other has degree 6. So if this is not true, that means that no vertex of degree 5 is adjacent to a vertex of degree 6. So that means my degree 6 vertices didn't receive any positive charge from vertices of degree 5 because they didn't have any degree 5 neighbors. So every vertex of degree 6 has charge plus 0 still. All right, that means, remember that when I redistributed, I didn't change the sum of the charges. We still have that the sum of the charges is equal to 12. So all of this positive charge has to come from the vertices at degree 7. These started as negative charges. So that means they would have had to receive enough charge from their degree 5 neighbors to make up for this. And it just doesn't seem likely. So let's establish that, in fact, we get a contradiction here. There's no way we can add up to 12. Excuse me. So let's think about a vertex of degree k. So let V be a vertex of degree k greater than or equal to 7. These are the ones we had to look at. So initially had a charge of 6 minus k, which we knew, was negative. So now let's think about how much charge it could have possibly received. So here's my vertex of degree k, and it's got these k neighbors. And since I have a planar embedding, I can lay them out like this, either like circularly around it, or I can just kind of lay them out all like this. I have k neighbors here. Now, since this is maximal planar, what this means is if I lay out the neighbors of V in this fashion, that two consecutive neighbors, well, they have to be adjacent because every region has to be bounded by a 3 cycle. So each consecutive pair of neighbors has to be adjacent in this planar embedding. Now, remember, by my rules that I'm assuming don't exist, we can't have two vertices of degree 5 that are adjacent to each other, right? No vertex of degree 5 is adjacent to any other vertex of degree 5. So, in terms of how this vertex could have gotten charge, well, it could have only gotten plus 5 from half of its neighbors, right? So if like this one is degree 5, then this one can't be degree 5. Then maybe this one is, then this one can't. And so at most k over 2 of its neighbors are degree 5. So V gets at most, it gets 1/5 from every vertex of degree 5, so it gets at most 1/5 times k over 2, so that's what, k over 10, at most this much charge. Right, remember the vertices of degree 5 are the only ones that are discharging, and so it receives at most this. And so now initially has a charge of 6 minus k, now has a charge of 6 minus k, and then it gets some charge, but how much charge does it get? It gets exactly k over 10 charge. Yeah, it gets exactly k over 10 charge, and so this is, so what? This is 6 minus, a charge of, at most 6 minus k plus k over 10. So that's 6 minus 9k over 10. But k is at least 7, right? So the charge is at most this, and k is greater than or equal to 7. So this is less than or equal to, so if k was greater than or equal to 7, 9k would be greater than or equal to 63. Divided by 10, that'd be greater than or equal to 6. So subtracting that, this would be 6 minus something greater than or equal to 6. This is strictly less than 0. So now every vertex of degree k greater than or equal to 7 has a charge of at most something strictly less than 0. So the sum of the charges is negative, but we know it's positive 12, and so this is a contradiction. And that concludes the proof. So this discharging has been used to prove other theorems. There's one in the book. There's an exercise. I don't believe I assigned it here. But yeah, this is a neat method for certain results. Okay, that was a long video. Sorry. I'll see you next time in the next video where we'll talk about a necessary and sufficient condition for a graph to be planar. See you there.